So in this lesson, we're going to discuss proving trigonometric identities. And if you're in my class, this is something that we've already looked at so far this year, but we now have some new identities that we're going to involve in our proof system. The questions we're going to work on today, we're going to talk about what an axiom is and how that has to deal with proving trigonometric identities. I have 3 proofs to do with you. And then we're also going to talk in between, we're going to talk about what are some general strategies for proving trigonometric identities that you can use. Okay, let's get to work. If you want to prove something in trigonometry and just in mathematics in general, then there has to be a certain facts or things that we're allowed to assume are true. For example, if I'm going to do anything in math, I'm going to assume that 2 plus 3 is 5, and there's really no arguing about that. These facts that we assume to be true in a proof system are called axioms. So in general, an axiom is a statement or formula that is understood to be true. When proving trigonometric identities, our axioms will consist of all the formula from our trigonometric identity page. So just to bring those up here, these are all the identities we've looked at so far this year, and you can use any of these identities in our proofs. We're not going to argue about these. We're going to assume that these are true. Unless we're specifically asked to prove one of them, we can use it in any proof we want. So I mean, all the ones that allow you to switch all your ratios to sine and cosine, all the addition and subtraction identities, the Pythagorean identities, and then these 2 new ones which don't get used very often, but you can use them, as well as all our double angle identities. And then again, not often used, but all our complementary angle identities, we're allowed to use those as well. We've proven all those formulas to be true, so they now become the axioms for our future proofs. And we have actually gone through, I believe, every single one of those together. Okay, let's look at our first proof. In this proof, we're going to prove that cosine of 2x plus 1 divided by sine 2x is equal to the cotangent of x. So I started by writing the left side and the right side down. One thing I know when doing proofs in trigonometry is that I only need sine and cosine. So when I see cotan, I know that really that can be expressed as cosine over sine. And that's the first thing I did with the right side. That's a simplified expression. There's nothing I can do with that. So it's probably pretty safe to assume we're not going to touch the right side any more than that. Moving over and looking at the left side here, I noticed that in the right side, I have cos x and sin x. I don't have a 2x here. There's no double angle. So the double angles on the left side, I'd like to get rid of those. I started by taking cos 2x and changing it to cos squared x minus sine squared x. Now remember, there are 3 different versions of the double angle identity for cosine. I just chose the first one, just randomly picked it. I've also put it in red so you can see the changes. Notice I didn't touch sine 2x yet. I'm going to do that on the next line. And the reason I've taken an extra line to do it is because I want to do a good job of showing my work. It is a proof. The idea is to show the steps and make it as easy to read as possible. So in my next step, I take sine 2x, and of course there's only one double angle identity for sine. Okay, it's 2 sine x cos x. And now it's not obvious about what to do. How am I going to make the left side look like the right side here? Well, I realized that the right side doesn't have any signs in the numerator, and I know that I can replace a sine squared x with a 1 minus cos squared x, so I'm going to do that next. After I've done that, I can start to clean this up. Now this is like a -1 here, okay, and I can sort of multiply through by -1. And when I do that, I get cos squared x minus 1 plus cos squared x, and then I can clean that up a little bit because the 1's are going to actually cancel out and the cos squareds go together. I get 2 cos squared x divided by 2 sine x cos x, and now I can divide by 2, and I can also divide, so those are going to become a 1, or divide out. I don't like saying canceling out. Think about what you're doing. You're dividing out. Can't just go canceling things. And I can divide out a cos x, divide the bottom of the fraction by cos x and the top of the fraction by cos x, so that I just get those right there. Now I'm This is kind of a mess and a proof. I'm actually going to like erase that even, and so it doesn't show up. That was just me showing you the steps there. Okay. And when I do that, I divide the 2's out and divide a cosine. I get the left side is equal to cosine over sine x, which is equal to the right side. And so the proof has been completed there. Now there is actually a quicker way that we could have completed this proof. And it has to do with the fact that we chose to take cosine of 2x and replace it with cos squared minus sine squared x. I could have instead said that cos 2x is equal to one of the other two identities, either 2 cos squared x minus 1 or 1 minus 2 sine squared x. I could have used either of those identities. And if I looked ahead here, I'd realize that, look, in the numerator here, I don't really want any signs because there's no signs in the numerator of the right side. So why introduce the identity that's going to introduce sine? Why not just use the one with cosine? Now let's just be clear, there's nothing wrong with this proof. It's perfect. I'm just going to present a quicker proof to you, a quicker method for doing this one. So here's a look at the quick method that we can use. So again, starts off the same with the left side. I'm actually not even going to touch the right side in this proof. Okay, so so my cos 2x this time, I chose to make it 2 cos squared x minus 1, or remember 3 double angle identities for cosine. And then right away I get 2 cos squared x over 2 sine x cos x, divide by 2, divide by cosine of x on the top and bottom of the fraction. And sure enough, you get cos x over sine x, and that is equal to cotangent of x. Notice I don't really need to change the right side, I could just change that to cotan. So there's another way to solve that same problem. Okay, let's look at our next proof. There's a lot going on both sides of this equation, but when I first look at it, I'm actually drawn to the right side first. And the reason I'm drawn to the right side is I immediately see a tan, and I know tan is sine over cosine. There's no tans over here. There's just really no reason to keep a tan in this one. So the right side is 1 minus tan x, which I'm going to replace with 1 minus sine x over cos x. This expression is actually not simplified. In math, we simplify by add, subtracting, multiplying, or dividing, whatever's possible. And I can actually subtract these two expressions from each other and make it into one rational expression. Okay, it's cos x over cos x minus sine over cos x, which gives me cos x minus sine x all divided by cos x. Now I know when I look at student work, a lot of times they're tempted to skip this step right here. I really like this step because remember that the idea is to make this as easy to read as possible. Can someone like me figure out why this is equal to this? Absolutely. Just like I can read without capitals or punctuation. That doesn't make it easier to read though, and this is easier to read when you include this step. Okay, so there's the right side. That's actually a simplified expression. It's all cosine and sine. It doesn't seem like there's much we can do with this. So let's take a look at the left side of the equation and see what we can do with cos squared x minus sine, all that stuff there. So here it is. Okay. Keeping in mind that I want to make it look like this. Well, notice that the right side and the left side, they do have some things in common. They're both one fraction or one rational sign, okay, and only with sines and cosines. Now this one is simplified. Is this one? As it turns out, it's not. Now it's not easy to see why it's not simplified. The answer is that for the same reason. 5/15 as an example. 5/15 is not simplified. Why? Because it reduces to 1/3. So it's the same idea with this equation right here. It's actually not simplified. Okay, now how do you see it's not simplified? You realize that you can divide the top and the bottom by the same thing when you factor the numerator and the denominator, and they both do factor. Cos squared x minus sine squared x is actually a difference of squares. So it's cos x minus sine x and cos x plus sine x. And then this cos squared x plus sine cos x has a common factor of cosine of x. So you factor out the cosine of x, you're left with cos x plus sine x. Just quickly expand those in your head if you want to double check that factoring's been done correctly. And sure enough, when we factor this, we do have these common factors that divide out. And we're left with cos x minus sine x over cos x, which is equal to the right side That concludes the proof. So this proof, we used a few strategies. We used the idea that tan can always be sine over cosine, and then actually, other than that, all we did is simplify. Everything else I consider simplifying. Putting this together is simplifying, okay? Factoring and then dividing is also part of simplifying. So now we're going to talk about some general strategies or tips for proving trigonometric identities. Now that we've looked at a few, what are the general, students always like to ask, well, how do you do this? I'm not good at it. How do you always know what to do? I'm going to give you some tips. The first one is express everything in terms of sine and cosine. It's not always something you have to do, but it's usually a good idea. Let's look at an example of that. In the proof we just finished here, that's exactly what we did here. We expressed tan in terms of sine and cosine. Simplify both sides of the identity. That's my next tip. So do any multiplying or dividing or adding and subtracting that you can do. Now, more specifically, that simplifying happens with rational expressions. And remember, pardon me, there are a few ways that you can simplify rational expressions. You might factor the numerator and the denominator to reduce. We had an example of that in our last one, which was right here, where we factored the numerator and the denominator just so that we could see stuff that would divide out. And then combine rational expressions by addition or subtraction, multiplication, or division. So that was also in the last example, where we combined 1 minus sine x over cos x into one rational expression. It's a good idea to remember that you only, in math, ever need one rational expression. You never, or one fraction sign. You never, anytime you have two rational terms, you can always put them together by adding and subtracting with a common denominator or by multiplying and dividing. So always can do that. Another good tip is always be looking at the other side of the equation to find out what your end result needs to look like. So an example of that was right here when I decided to replace, let me just erase this here, to replace sine squared x with 1 minus cos squared x. I decided to do that because I looked at the right side. I didn't see any sines or any sine squareds in the numerator, so why not try to get rid of them here? I thought that that would be a good idea. And I also used the idea here. When I knew to use the double angle identity, there were no double angles on the right side of the equation, so use the double angle identity to get rid of them on the left side of the equation. So I'm always looking at both sides and realizing what am I trying to get to and what does it make sense to do based on that. It's kind of like in trigonometry, you know the answer, you're just trying to get there. Keep this tip in mind as we look at the next two tips as well. Remove double angles using double angle identities where appropriate. So just like the example I showed you, I used a double angle identity because I saw no double angles on the other side of the equation. So that's how you get rid of them. And then sometimes you can use the sum and difference identities. Those could be involved in proofs as well. And then replacing sine squared x with cos squared x or vice versa using the Pythagorean identity. It's a good idea you don't always replace sine squared x with cos squared x. You don't always replace cos squared x with sine squared x. You use this tip right here to decide when it's appropriate to do that by looking at what your goal is and what you're trying to do. Okay, maybe you can also try doing it, and if it doesn't work, then just drop it and try something else, but always be looking at the other side. And I can't stress this enough. Show each step clearly. Everyone knows the final answer, so the important aspect of your solution are in the details. Okay, I shouldn't have to sit there when I'm reading someone's proof and jot little calculations in to check their work. The work should all be there in very, very simple steps. It shouldn't be a struggle to follow a good proof. And there are usually several methods for proving a trigonometric identity. There are lots of solutions. Just because someone else has done something different doesn't mean that you are necessarily wrong. There's lots of ways to do these. Okay, let's look at another example. So we looked at double angle identities in this course. Take a look at this proof. There's actually a triple angle here, the sine of 3x. Okay, now is there a formula for a triple identity? Well, not really. I mean, I guess there is. It's right here. In this proof, you're actually kind of finding your own identity for a triple angle for sine. How do we do this? This one's actually kind of tough to get started on, which is why it's a good example to look at. Do I want to work with the right side or the left side? Well, notice that on the right side, there are no 3x's. It's always sine x or sine cubed x. So we really don't want that 3x here. So let's look at how we can change the left side of this equation. Here's a little trick. 3x is really 2x plus 1x. And then we can use the sum identity for sine. So remember that sine a plus b is equal to, I'll even write it down. Sine a plus b is equal to sine a cos b plus cos a sine b. Now in this example, our a is going to be 2x, okay, and our b will be x. So we're going to apply that formula, and we get sine 2x cos x, sure enough, plus cos 2x sine x. Now, the right side of the equation doesn't have any 2x's in it either, so we really don't want these 2x's here. But we have double angle identities to get rid of those, so let's use those next. Now, I use the double angle identity for sine 2x. Okay, notice it's in red here. The changes are in red to try to make it easier. So sine 2x is 2 sine x cos x. So I get 2 sine x cos x times cos x. So this cos x is from here, and all this stuff is from the sine 2x. Okay, I'll underline the whole thing there. I did the same thing with the cosine of 2x. I need to replace it with a double angle identity. Now I had 3 choices, remember. Look at the one I chose, though. Can you think about why I chose to use 1 minus 2 sine squared x and not, say, cos squared x minus sine squared x or 2 cos squared x minus 1? Again, I'm looking at the right side of the equation. There are no cosines on the right side of the equation. So if possible, I don't want any cosines. So why not choose the one that just involves sine? Yes, I have some other cosines as well, but I can deal with those later. I'm sure if you picked a different one, you could still do this proof, but this is just I know that this is going to work out the best. I'm just going to clean this up now. Multiply this stuff together, and you get 2 sine x cos squared x. Cos x times cos x is cos squared x. And then I'm going to multiply everything in the brackets by sine x. So sine x times 1, which gives me sine x. Sine x times negative 2 sine squared x gives me negative 2 sine cubed x. Okay, once I've done that, now what? It's not obvious about what to do. Well, I can look at the right side again and realize there's only sines, and sure enough, I have a cosine here, but it's a cos squared x, and that's fine because I can replace cos squared x with 1 minus sine squared x. Just like that. And then again, I'm going to keep, anytime you can simplify, it's always a good idea. I'm going to multiply 2 sine x by 1, then I'm going to multiply 2 sine x by negative sine squared x. So I get 2 sine x minus 2 sine cubed x. I've got some like terms. I got a 2 sine x plus a sine x. I got a negative 2 sine cubed x and a negative 2 sine cubed x. Gives me 3 sine x minus 4 sine cubed x. And sure enough, left side equals right side. We're done the proof. That's that's sort of a new one, a little bit more challenging. Okay, and this little trick right here at the very beginning really helps you get started. Okay, thanks for tuning in.